Now we've got these wonderful machines called airplanes, and they are designed for a certain lifetime. The design criteria might involve landings and takeoffs, pressurization cycles, gust loads, maneuvering loads, other conditions. And we generally find that these aircraft will live up to those lifetime designs, even though they may require significant maintenance from time to time. We have, if you've read in the papers or listened to TV lately, an issue, however, with a lot of our military aircraft that are deemed currently unfit to fly, even though they may not have yet exceeded their expected lifetimes. They can't be salvaged by just routine maintenance. We have to do what is sometimes called life extension. That is, they may be approaching their design lifetime, but we want to use them for another 20 years or another 30 years. And so we have to extend that lifetime. So the ability to keep our aircraft flying through regular maintenance, and that means very good manufacturing procedures as well as good design, and then continuing their life for a long time to come. We have B-52s flying that are over 70 years old, and we couldn't keep those airplanes or high-performance other military aircraft continuing to perform their functions if we did not have these advanced techniques for extending their lives. Mr. Luciano Smith, engineer, structural engineer for aircraft structures at Southwest Research Institute. Either one.
Either one, okay. Well, thank you, Norm. So this is the title I submitted a few weeks ago, and after submitting it, I decided it was kind of bland and boring, so I wrote another one. This one's a little more specific, has hopefully bigger words that impress you or distract you. But in thinking about what's actually interesting about the work we do, I decided to go a different direction. So I decided to go with breaking stuff to keep planes flying safely, because who doesn't like to break stuff occasionally? So let's dive into that. So I was asked to speak about what's going on and what's needed in aerospace manufacturing and life extension research, and came up with a few examples of a few prominent research areas that get a lot of press recently, things like durability of composite structures, embedded sensors for structural health monitoring, and additive manufacturing, which you probably hear referred to more often as 3D printing. And there is a lot of valuable research going on in these and other areas, but I wanted to focus my time on a little bit less prominent area, and I'll explain why. So I'm going to talk about today's aircraft fleet. The two plots on the left give a snapshot of the percentages of different materials used on most U.S. Air Force airframes, with the newer airplanes further to the right in both plots. The dark gray, the black, and the light gray are all metals, and the two lightest colors are composites and others. And you can see that there is some correlation between when an aircraft was designed and how much metal is used and how much composites used. But even the newest planes have a large amount of metal. The chart on the right shows similar information for the commercial fleet with the percentage of composites in each airframe. And again, the amount of composites has increased as time has gone on, but there's a question mark on the right, and the context of the presentation that I pulled this from imply that composites in general are not expected to increase beyond about 50% of the material used. So not only do newer aircraft still include a significant amount of metal, but we also still have many old aircraft flying, especially in the military. Like Norm just mentioned, we've got planes flying that are as old as 70 years old. So these two facts have a significant implication in terms of life extension. Metal fatigue has been a critical issue in terms of aircraft maintenance, and it will still be a critical issue for both airframe manufacturing and life extension because of these two issues. So because of that, we have a lot of ongoing research programs related to aircraft fatigue. I'll mention a few here and then focus on a couple for the remainder of my time. The first is NASGRO, which is a fatigue crack growth software. It's used to determine how quickly cracks will grow through these critical areas. The second is Darwin, which has a similar goal, but also includes probabilistic features to allow users to calculate probabilities of failure over time. The third is ERSI, or Engineered Residual Stress Implementation, which is a working group developed for incorporating residual stresses into these types of crack growth analyses. We're also working on developing inspection methods to find smaller and smaller flaws in structures, such as this method right there for looking through bushings into the second layer structure for cracks using low-frequency eddy current. We have a lab dedicated to solid and fracture mechanics where we determine material properties and grow cracks in various environments and conditions. And we also have a lab used for full-scale testing of full aircraft and structural components, and we can also use that for development of structural repairs and repair procedures. As an example of some recent full-scale testing, it's a T-38 wing test where we attached T-38 wings to a fuselage, hung it upside down in a steel frame, and cycled the wings using hydraulic actuators with the actual loads that we recorded from flying aircraft. This testing is used to determine the lifespan of the structure, with the usage being flown today, so that any unknown critical areas become apparent in test rather than in the fleet. After thousands of simulated flying hours, you can see that a crack developed in the lower wing skin and grew to failure. And that skin's over half an inch thick. It broke with pretty good bang. The T-38's been flying for over 50 years, and tests like these ensure it can keep going safely. So I mentioned NASGRO earlier. This was first developed to provide fracture control analysis for NASA manned space programs in the 80s. And the first NASGRO consortium was formed by SWRI in 2001. And in the years since, a lot of work has been done to grow the program to include 5 separate modules, including things like crack growth analysis, boundary element stress intensity computation, and crack initiation analysis. And the consortium has also grown over the years. Now includes a number of quite prominent and significant companies in aerospace, in addition to NASA, who's still heavily involved, both technically and in funding. This slide gives you some insight into the crack growth module, which allows the user to select a fracture mechanics model that best represents the critical location, some material properties to model the crack propagation, the loading spectrum to simulate the aircraft usage, and finally to run and visualize the results. Every aircraft structure develops cracks, and this allows users to know how long a crack will take to grow to failure and to plan inspections and maintenance accordingly. One of our most important roles in the ongoing research that continues to improve NASGRO is the development of new fracture models that accurately represent the geometries and loading felt by critical locations. This gives users a consistent, accurate, and simple method for modeling these locations, which would otherwise require development of costly analytical models. So the next program I wanted to talk about was Darwin. Darwin's another fracture mechanics-based fatigue crack growth code. It was originally developed for gas turbine engine components and has since been generalized for other types of parts. It allows users to link to analytical models and can be used to determine crack growth life and probabilities of failure. Primary funding for this has come from the FAA, with significant funding also coming from other sources, including all the major aircraft engine companies. So this slide gives a summary of the inputs and outputs from the program. Like in NASGRO, the user inputs fracture models and material properties. And then for the probabilistic portions of the calculation, the user inputs also distributions of anomalies or flaws that can grow to become cracks, inspection schedules, and also probabilities of detection. It's the probability of those inspection methods detecting flaws of different sizes in the material. And with all those inputs, the program calculates probability of failure versus loading cycles to show the user whether the current inspection protocols will keep the component flying safely beyond the planned life. One recent addition to the program is the ability to perform the fracture risk calculations in additive manufactured parts, which can be more susceptible to cracking than parts built using conventional techniques. Part of this functionality is the ability to link Darwin with X-ray simulation software to map anomalies within the material and determine the risk of them growing to failure. The final research program I want to highlight is our work in support of engineered residual stress implementation. At the request of the Air Force, we started a working group in 2016. And a little over a year in, we have 78 individuals involved from a wide variety of organizations. This cover slide from a coworker's recent presentation at the U.S. Air Force ASIP conference shows the breadth of the involvement. So I'll start off covering the goal of the work by defining residual stresses for those who are uninitiated. Residual stresses are stresses that are locked in a material without the presence of an external load. They can result from a few different types of processes during and after the forming of the part. Some manufacturing processes that cause residual stresses include forging and rolling. The picture on the top right there shows how the rolling process creates a large compressive stress near the surface and small tensile stresses underneath. And then other processes that cause residual stresses include those such as welding and peening that are after the initial manufacturing. The picture on the bottom shows distortion caused by the stresses from heating and cooling a metal during a welding process. So that's an example of undesired residual stresses. But other times, residual stresses are designed into the part. One example of a process performed only to introduce residual stress into the part is cold expansion of fastener holes. So the picture on the bottom left shows how this is performed. A mandrel with a sleeve is put into a fastener hole, and then the mandrel is pulled back through the hole with the sleeve kept in place. Because the end of the mandrel, shown here, is bulbed, it pushes the sleeve into the material around the hole, stretching it to a larger diameter. This stretching causes the material at the hole to have a large compressive residual stress, which is shown in blue in this center plot here. The large compressive stress squeezes flaws in the material, making it more difficult for them to grow as fatigue cracks. So the plot on the bottom right shows crack length versus loading cycles. As an example of test data showing the difference between crack growth at a cold worked hole and at an identical hole without the cold working. So you can see that the crack at the cold worked hole, shown over here, is significantly slower than the crack at the non-cold worked hole, which looks almost vertical on the scale here. So we know that cold working holes causes fatigue cracks to grow much more slowly, but we schedule maintenance based on the expected crack growth. So in order to take advantage of that benefit in our maintenance processes, we have to incorporate cold working into our analyses somehow. So how's that done currently? Well, Air Force guidance on incorporating cold working into analysis, which was written over 30 years ago, is to start your crack growth analysis with a smaller crack size and make no other changes to the analysis. This does increase the analytical life of the crack, as shown in the plot on the right, but it doesn't incorporate the physics of the residual stresses at all. We know we can do a lot better than that with the capabilities we have now. On the commercial side, in general, the benefits of cold working are not taken advantage of at all in the analyses that determine the maintenance processes. Safety is improved, but maintenance costs are not. So how can we best incorporate the actual physics of the cold working in order to benefit both safety and costs? So the Air Force leadership has led us down a path that incorporates a handful of different questions to be answered. These are not all of them, but here's a few examples. So first of all, quality assurance. Was the hole actually cold worked as required? We and others are designing tools that can validate whether it was, so we know whether we are getting the safety benefits that we're planning for in our maintenance scheduling. Secondly, what effect does cold working have on inspection methods? Residual stresses keep cracks closed, slowing growth, but they also make it more difficult for inspection methods such as ultrasonics to see those cracks. The Air Force is doing research to make sure we understand this effect. Next, is there significant variability in the residual stresses that can affect crack growth? Or to put it another way, will a small change in any of our inputs cause a large difference in crack growth lives? If so, we need to understand that so we can be conservative in any of those areas and not overestimate the time it takes for cracks to grow. And then finally, do we have analytical methods sufficient to determine the impact on crack growth life? We need to be able to model the process and understand the stresses in the material and how those stresses affect growth. So these next couple slides cover work we performed recently in support of the uncertainty quantification and analysis aspects of ERSI. Measuring residual stresses due to cold working is a complicated process, which is actually measuring, what is actually measured is the displacements on the scale of microns, which are then analytically turned into stresses. And there are many potential sources of error and variability, so we've done work to determine the single measurement uncertainty, shown in black in this plot, and the repeatability uncertainty of the measurements, shown in red. So once that was understood for the geometry we were looking at, we had cracks grown in our specimens to different sizes, and then those specimens were cut and the residual stresses measured to see whether the residual stresses change in the part as a crack grows. So the plot on the left shows that they do. The red line, which is the lowest line, shows the stresses through the thickness for the uncracked specimens. Those stresses average about negative 40 KSI through that thickness. And as the crack grows, the different black lines above it show that the stresses decrease as the crack grows to an average of about negative 30 KSI for a half-inch crack. So incorporating these different stresses into our fracture models at the different crack lengths allows us to determine what the crack growth lives might look like. The red lines show the growth of 3 cracks in test specimens, right here, these 3. And then the black lines are analytical comparisons using the average residual stress field as well as up and down 1 standard deviation to understand the impact of variability due to the measurement uncertainty. You can see that in this case, our 3 analytical, or our max and min analytical comparison do bound the 3 test results. So where are we going with this? We're working with the Air Force to develop a document with 2 goals. First, to dictate the methods required in order to account for the benefits of cold working, and secondly, to provide examples of best practices for others to be able to use. There's also some potential for this work to be transitioned to a standards organization like ASTM and generalized to other residual stress methods and other industries. So to sum it up, there's a lot of good work being done in aero manufacturing and life extension, both in some prominent areas as well as some areas that are maybe a little less glamorous. But we believe that the breadth and the prominence of the customers and the organizations involved in each of these areas just show that their value is significant and that there's still a lot of good work to be done.
Thank you, Luciano. Good. Questions? Yes.
I was wondering, when you move away from metal and start going to composites, you can't use eddy current or magnetic particle to do your inspections, and you start moving towards like X-ray or ultrasonics. Mm-hmm. Has there been any research on what those type of inspection methods, how it would affect the composite over the life of the part?
That is not something I'm aware of. I'd like to say yes or no, but I don't know.
Anyone else? Any questions for any member of our group of speakers? Yes, sir.
You're talking about the stair-step development process. Yep. Where does Aurora fit into that?
Well, let's see, I first learned about Aurora in Aviation Week somewhere around, 1990? So it's far to the left of the slide.
Okay, anyone else? Okay, ladies and gentlemen, when we were planning this session, I confess that I had some trepidation that we would have a group of people from business and a group of people from research, and their interests and viewpoints would not mesh. And I'm so happy that I was wrong. I feel like we've had an amazing display of common interest, common goals, and very, very good interaction between business and research, academia, all of these activities in the aero field in our state. So I want to thank all 9 of our speakers, each one of whom was articulate and very comprehensive in their presentations and did such a wonderful job. So thanks to all 9.